So let's talk about the electric field. So we're going to talk about what the electric field is, then we're going to work some examples. So like most things, it's pretty good to know what you're talking about. So the electric field is the force per unit charge that a positive charge would experience. Which is to say that if you had a positive charge at some point P, and you have all these other charges, we'll call this Q1, Q2, Q3, the electric field is equal to the force. And in this case, you've got more than one, so we'll say the sum of the forces over Q test. This test charge is a hypothetical charge, which would be the charge that you would put right here at point Q. So if we expand the forces, it would be the sum of K, Q test, Q, I'm just going to call this Q other, over R squared, over Q test. If we look, these two Q's will cancel out, and you're just left with K, Q other, over R squared. And that is your formula for the electric field. Keep in mind that this is a vector, right? And so we have this little hat. So you need to add this exactly like vectors. Also, to keep in mind that the Q test, your test charge, whatever charge you put at point P, doesn't need to enter this at all. So you don't need to mess with it. That's kind of nice. It can be a positive charge, it can be a negative charge, big charge, little charge. The electric field is going to be the same because it just tells you force per charge a positive charge would experience. To calculate force, you need to figure out, what charge you put there. We'll do that later. So let's go over some of the rules about mapping a field line. It's the force a positive charge would experience. So if you think about it, a positive charge would go away from another positive charge. And we can draw that like this. Okay? Now, something to note. If you have a bigger charge, you get more field lines. More charge, more field lines. And your field lines never cross. I don't know if this reminds you of anything, but it always reminds me of the Stay Puft Marshmallow Man from Ghostbusters. Due to copyright infringement, I didn't want to put the actual Stay Puft Marshmallow Man here. So I put this guy. He's in s'mores. He's more threatening in the movie. Alright, so in this one, I'm going to call this minus 2Q. Again, you're going to go from positive to negative, and I want you to sketch what happens over here. Pause it, sketch it. Got it? Alright, let's see how we did. Alright, so in here it's going to repel, and it's going to repel from here too. But when they repel, they're going to get attracted by this one, so it's going to come in and come in. Or if it wasn't strong enough, it'll go out and out. And let's go again. And this one's just going to go out here and out here. There are more field lines going into this. Why? It's a bigger charge. And I guess we can also, here I'll draw two more over here so I can draw something out here. Okay, so now let's, alright, so in this one, I'm going to call this minus 2Q. Again, you're going to go from positive to negative, and I want you to sketch what happens over here. Pause it, sketch it. Got it? Alright, let's see how we did. Alright, so in here it's going to repel, and it's going to repel from here too. But when they repel, they're going to get attracted by this one, so it's going to come in and come in. Or if it wasn't strong enough, it'll go out and out. And let's go again. And this one's just going to go out here and out here. There are more field lines going into this. Why? It's a bigger charge. And I guess we can also, here I'll draw two more over here so I can draw something out here. Okay, so now let's work some quantitative examples. So let's set up this problem. You want to find the electric field at this point, P. So if we look at this, we know that the electric field equals the force per charge at point P, which equals, that's just the test charge, remember, test charge. Doesn't actually factor in anywhere. So this would be K, Q other, everything not at P, R squared, and then R hat. This indicates the direction a positive charge would go. In this case, positive charge is going to be repelled from this 2 coulomb charge. So if we plug in all of our numbers, you get your electric field equals 9 times 10 to the 9th Newton meters squared per coulomb squared times that charge of 2 times 10 to the minus 6 coulombs all over the distance between them, which is 0.1 meters squared. And then just put that there for the direction. You get that your electric field is 1.8 times 10 to the 6th newtons per coulomb in the y hat direction. So the direction comes from what happens, what's going to repel, a positive charge would repel from this 2 coulomb charge. Even though this 10 to the 6th seems really big, the charge on a single electron is really small. So you need a ton of electrons to make this work. How would this change if you had a negative charge at point P? That's right, it's not going to matter at all, because this is only the charge from everything else. Whatever charge you're thinking of putting at point P, it doesn't matter. And that's the perk of working with the electric field. So let's try another example with vector components. So in this problem, we're going to calculate the electric field, but we have 2 charges. So the electric field from this minus charge is going to actually point, well, it's the way a positive charge would go. Positive charge would be attracted here. So this would be, we'll call this E minus, and a positive charge would be repelled from that one. So we'll call this E plus. Now, in this problem, we're going to use vectors, but let's use a little bit of symmetry. You know that this angle right here I'll put them in yellowed, is equal to this angle. So the only component you're going to care about is going to be the x component. So you only care about the x component. So let's get the x component, and I'm going to start with the x component from this 2 microcoulomb charge. So let's take a look at this. I'm going to zoom in the picture a little bit. So if we're interested in this E plus, and we want to find this is the E plus in the x direction, you know that you need to know the distance between here. In this case, this would be the square root of 0.2 squared plus 0.1 squared, which equals 0.05 meters. So if you're calculating this, the total E equals, from the plus charge only, this would be 9 times 10 to the 9th Newton meters squared per coulomb squared times the charge, in this case this is 2 times 10 to the minus 6 coulombs, make that 6 a little better, over 0.05 meters. But you care about the x component, so that's why I added this little x right here. And to get the x component, you want the side adjacent to that angle, so using trig, that is cosine of theta. So let's take this, scooch that over just a little bit, and let's look for what theta is. Well, cosine of theta, this angle right here is going to be the same as this angle. Cosine is adjacent over the hypotenuse. So I'm just going to cross out this cosine and replace it with adjacent 0.2 over 0.5 meters. So if I plug this in, I will get my x component to be 6.44 newtons per coulomb. And what direction is that? That is in the negative x direction. So the way I got that direction is I drew my picture. Always draw a picture. You'll see it points away and in the x direction. Likewise, if I use the symmetry argument, I could say that, well, this here, let's do this in, we'll do the negative in red. You know that the negative side right here, they're the same magnitude, so it's actually going to give you the same number, and you can try this out. I'd also like you to verify that the y components cancel. So if you get this, your total electric field, E total, is equal to negative 12.88 newtons per coulomb in the x-hat direction, which means it's going to the left. So this is an example using symmetry, using vectors, breaking things up into components. Again, always use this distance. Always use the actual distance. Don't break it up. One more example. Now in this case we've got a ball and it's levitating. So it's balancing. There's some electric field. Let's put the electric field this way. And you know that the force is pulling down. You've got gravity pulling down, and you've got some electric force pushing it up. Now, the electric force is Q times the electric field, and it's not going anywhere. It's not accelerating, so we use Newton's laws. Sum of forces equals ma. It's not accelerating, so you get your QE minus mg equals 0. Solving this, you get QE equals mg, or your electric field is equal to mg over q. This is just balancing the forces, but the important part of this, A, always use Newton's laws. They're nice drop force diagram. And B, sometimes you have to use this expression for the force caused by a particle in an electric field. So I hope that helps. And I will see you in class.